We now turn to the statistical description of quantum systems with a macroscopically large number of particles. This is a setting of thermodynamics where we talk about properties such as the entropy, internal energy, temperature, volume, pressure, particle number, or chemical potential of the system. What we want to understand is how these properties emerge out of a microscopic description. This microscopic basis of thermodynamics is statistical mechanics, with the crucial ingredient being the Boltzmann distribution. According to this, a thermodynamic system in equilibrium occupies its available states with a probability that involves the exponential of the ratio of the energy of the state, EI, and the temperature T. In here, K is the Boltzmann constant, which simply converts temperatures into energies, and the minus sign makes sure that the probability decreases as the energy increases. Finally, Z here is a normalization factor known as the partition sum. From there, we can, for instance, develop thermodynamics by starting from the Gibbs entropy as specified here. We can assign an energy to states already on a classical level, and so we should ask where quantum mechanics comes into this. And then we realize that it enters in several ways, with the most important one being to give a precise notion of the available states, both through quantization as well as through the symmetry constraints when we deal with indistinguishable particles. The question of how to define and count the states was indeed a crucial point that held up the development of statistical mechanics in a notable way. When Boltzmann introduced his ideas in the 1870s, they were firmly connected to a microscopic picture of matter made out of discrete entities, such as atoms or molecules. And he even suggested that the energies of a physical system may take discrete values, while in classical mechanics these energies vary continuously. But such concepts were at the time controversial. Indeed, even the existence of atoms was not widely accepted for another 30 years. And anything beyond this, including the consistent way to determine discrete energy levels in quantum mechanics and the developments around the Pauli exclusion principle, only could follow afterwards. But now we do have quantum mechanics, and it provides us with all that we need in a highly accurate and practically useful fashion. We even can count states when their energies are continuous, as we have demonstrated when we derived densities of states for various types of particles moving in a given number of dimensions. Indeed, we could formulate this all in terms of a density matrix, as specified here, where we have the Hamiltonian in the exponent, and the partition sum is the trace of this expression. And with this we could even tackle interacting systems. But here, as before, we are going to assume for simplicity that we deal with non-interacting particles. When we would start with freely moving, distinguishable particles, this gives us an ideal and essentially classical gas. And when we consider indistinguishable particles, this becomes a variant of such a gas, a Fermi gas or a Bose gas. But we can also apply these considerations to collections of particles that do not move freely, such as electrons moving through a solid or atoms trapped in a certain potential, and in many cases we can then still ignore their mutual interactions for the physical effects that we are interested in. With this assumption of independence, we can again resort to specifying the occupations of the states. And we now want to do this on average, where this average is derived from the Boltzmann distribution. So we really treat this as an additional prescription of probabilities to occupy the states. So we are going to utilize the Boltzmann distribution, these densities of states, and further constraints such as the Pauli exclusion principle to explore the consequences of the interplay. In the case of fermions, the Pauli exclusion principle tells us that the possible microscopic occupations are 0 and 1, and so the average occupations will lie within this range. And using the ingredients described above, it then turns out to be of the form given here. This is known as the Fermi-Dirac distribution. The detailed derivation does not concern us. Indeed, it can be derived using different statistical ensembles, and as always, this will be covered in more specialized courses. What is important for us is the result, and what requires explanation in there is the appearance of the chemical potential mu. So let me briefly comment on its origin. The number of particles in the different states fluctuates. Think of fluctuations of the density in different parts of the system, but we can think of this also in terms of these states. This amounts to an exchange of particles between the states, which in thermodynamics is regulated by this chemical potential. Essentially an additional energy attributed to the mere existence of a particle. So taking this into account, one then finds the stated expression. The chemical potential is then fixed by requiring that these average occupations add up to the average total number of particles in the system. And analogously, the temperature is fixed by requiring that these resulting energy contributions add up to the average total energy in the system. The role of these two parameters becomes clear when we sketch the average occupation as a function of energy. This is close to 1, so fully occupied for energies sufficiently below the chemical potential, and close to 0, so fully unoccupied, sufficiently above the chemical potential. The energetic region where the average occupation changes significantly is of the order of kT. Often one says it is about 3 or 4 kT. There are two interesting limits, that of a small temperature and that of a large temperature relative to the other energies in the problem, while keeping the number of particles fixed, at least on average. In the limit of a very large temperature, the energetic range of partially occupied states spreads out to the extent that even the ground state is barely populated, as the chemical potential will have dropped below it. We end up with a so-called non-degenerate gas, for which the Pauli exclusion principle isn't very relevant. The Fermi-Dirac distribution then indeed approaches the corresponding distribution of a classical system, which in this context leads to the so-called Maxwell-Boltzmann distribution. In the limit of a vanishingly small temperature, the Fermi-Dirac distribution approaches a step function, so changes abruptly from 1 to 0 at the limiting chemical potential. This value is then known as the Fermi energy. And in this scenario, all states below the Fermi energy are completely filled once, according to the Pauli principle, while all the other states are empty. This reminds us of the way we filled hydrogen-like atomic orbitals when we discussed the periodic table of elements. And with our considerations here, we can now scale this picture up to macroscopic systems. For example, take the electronic states in a solid. You can look at these arising from the states of atoms that change as they are being brought closer together. The states then tend to cluster into continuous regions, so-called bands, separated by gaps. And now the electronic properties of the material depend principally on how these bands are being filled by the available electrons. Because there are so many electrons, the chemical potential will be very large, much larger typically than the temperature. Therefore, the latter is relatively small, so that in the first instance we can say that all states are filled up to the Fermi energy. And now this Fermi energy can lie either within a band, which is then partially filled, or all bands are completely filled or empty. We then say the Fermi energy lies in the band gap between the filled band highest in energy, the so-called valence band, and the empty band lowest in energy, the so-called conduction band. Well, in the case of a partially filled band, it does not cost much energy to excite an electron to another state in this band, where the extra energy may come from the finite temperature that smooths out the Fermi-Dirac distribution in that energetic region, or may be supplied externally by applying, for instance, a voltage difference. In this excited state, the electron can then move around relatively freely. So this would be typical for a metal. In the other case, where the bands are either completely filled or empty, the energetic costs of such excitations are high, and so we have an insulator or a semiconductor. In semiconductors, we can further modify these electronic properties by introducing some extra electrons by the addition of other chemical substances, a process that we call doping. These additional electrons then occupy the bottom of the conduction band and then move again relatively freely. Indeed, they are typically well described as effectively free electron-like particles, but with some adjusted properties, such as their mass. Analogously, introducing doping by some other substances, we can also remove electrons from the system, and the remaining vacancies in the valence band then behave as effectively positively charged particles, so-called holes. The filled and empty bands may also touch at a point where the density of states drops to zero. This then defines a semimetal, and one example of this is graphene. Furthermore, when one makes the energies in the bands dependent on spin, one can, for instance, obtain an effective description of ferromagnets. These considerations can be made quantitative when one determines the band structure quantum mechanically. However, this generally requires advanced methods, as interactions cannot be neglected in such calculations. There are also systems in which these considerations break down. These are characterized by very strong interactions and are known as strongly correlated materials. For instance, high-temperature superconductors fall into the latter class of systems. But as we will briefly discuss below, superconductivity, even conventional one, is really related to bosonic physics. So we come back to this very soon. Let me just mention one more extreme case of a highly degenerate Fermi gas, namely a neutron star. As the name implies, this is made out of neutrons which are heavily compressed under gravity. This system is then stabilized by the Pauli exclusion principle. In the language of a gas, one can translate this into a pressure, the so-called degeneracy pressure. And that pressure is large enough to prevent the gravitational collapse as long as the neutron star does not exceed about 3 solar masses. If that occurs, the neutron star will collapse into a black hole. The formation of a neutron star itself follows a similar mechanism when we start from a sufficiently heavy main sequence star. The core of such a star is stabilized by the degeneracy pressure of the electrons until it exceeds the Chandrasekhar limit of about 1.44 solar masses. So once this occurs, the star collapses into a neutron star or further into a black hole. On the other hand, when a main sequence star burns out with the core below this mass, what remains is a white dwarf, and this remains stabilized by the electron degeneracy pressure. So this defines a few different evolutional endpoints of main sequence stars.